So today I will talk about augmented reality for Qt. Namely, I'm working at a university in Switzerland, and we are using Qt extensively, and specifically we are using it for augmented reality. So why are we doing this? We want to work in classrooms because our lab cares for learning, but in general, the techniques that we develop, they can be used in other applications too. So this is the Github of our lab, and today we will talk about qml-ar, which is an augmented reality library. But over the years, we have developed a lot of libraries which replace missing functionality from Qt. Namely, we have a library for IMU on Android. We have a library to log data. We have a library to cache data from QML. And yeah, we have many more. And yeah, even more than that. So, but for today, the goal is to develop a library for augmented reality. And the goal of this talk is to first show how easy it is with Qt. And so I will show you how many problems arise when one tries to develop a library for augmented reality. And I would say that a lot of these problems were much less severe because we used Qt. Yeah, this is one of the constraints because a lot of applications in the lab are already written in QML, and therefore we want compatibility. And another constraint is that we want it portable, meaning that we want it run on consumer-grade tablets. So the solution is that, yeah, I forgot to say the most important part, that we don't want conventional markers, which are QR code-like black and white rectangles with pixels, because they are very visible. They are made specifically to be visible so that it's easy to detect them using vision processing techniques. But they're also visible for the human eye. And immediately when one looks at the scene with these markers, they attract a lot of attention. And specifically for our application for classrooms, it's not desirable, but we imagine that for other applications, it could be that it's also important that markers are pretty and looks nice. So how to achieve all of these criteria? We came up with the following strategy. We are taking existing project for augmented reality using some unconventional markers. And usually the issues with them is that it's research code, meaning that it was written once to as a proof of concept, but it runs pretty slow. So what we do here today, we take one of these libraries and we try to run it really fast. So yeah, my talk will be 45 minutes. We'll talk about some motivation and goals. We did that. And then later I will talk about design choices that we make and about the performance and tools. Like I think for this, maybe for this audience, tools would be most important because I will describe how we use Qt and why is it important. And finally, I will demonstrate to you how it works. I don't have a live demo today because my phone doesn't have the latest version of Android, sorry. But yeah, I have some videos. So yeah, should be interesting. So first of all, what do we want to solve? We want to estimate the pose of the phone using its sensors. And there are a few approaches for that, but each of them has its problems. None of them is perfect. So for example, phone has an IMU, which is usually a gyroscope, compass, and accelerometer. But the problem with this is that it does not give you an absolute location. Another possible solution is to use some electromagnetic waves like Bluetooth, but the problem is that the precision is not quite high. Also, another solution is to use markerless augmented reality, but the issue is that we also cannot we also cannot obtain the absolute pose, meaning that it's relative to the image that we are obtaining. So the only way that works for us is to use markers. But again, as I told you, conventional markers don't look great, and therefore we want some unconventional ones. So yeah, if you try to search for unconventional markers, this is what comes to mind. So there are really a lot of ways to do this, but all of them use the following approach, namely there is a high contrast image and there are some blobs, and these blobs are located in such positions that they encode once they are detected, they can be used to infer the pose. So we will also use that, but we will try to make it seem less visible. So these ones are visible because, for example, this one has a very distinct shape. It's a circle, and this one is a square, and therefore, if it's on a scene, it's really clear that there is a marker, and it takes a lot of attention, and it drags the user away from the task that he's trying to solve. So let's go next. So what are the constraints for our markers? We want it to be agile, meaning that it should be applicable to any scene. So, for example, for these ones, the problem could be that a specific color is already present on the scene, and therefore it's not possible to use this marker because it would not be possible to detect it on a scene that already has this color. So far, we have only one winner, and one of the reasons is that we were trying to search for an existing implementation for this code, and this was the only one that we could find. And so we are seeing some kind of a trade-off between how much seamless a marker is and how much well-detectable it is, meaning that the easier for a camera or for a computer vision program to detect it, the easier for human eye to detect it. So we have to choose some sweet spot in the middle. Right, and if we move to seamless markers, which explicitly try to be less visible, there are already a few approaches, and here we take, again, only one of them, because only for this one we have found existing code. So, and now the question is, how do we implement it, and how do we integrate it with Qt? So, what kind of code is it to begin with? It is a proof of concept code that worked once for the researcher and which goes with the paper, but it's not very performant, and it definitely does not run on Android, and it definitely is not integrated with Qt. So if we try to integrate it, we need to use some framework, because it's not a good idea to write everything from scratch. So there are already existing AR frameworks, such as AR Toolkit and others. However, we have failed to find a clear way to take a new marker type, integrate it with Qt, and with that framework. Specifically because there was a lack of NDK support. Maybe somebody in the audience would correct me, but when we did this research, it came up that none of these libraries can support Android NDK and Qt together in a good way. Yeah, so we don't have a perfect solution, and therefore we decided to just use plain OpenCV. And I must say that it's integrated with Qt quite well. For example, there are primitives which allow to convert a CV image to a Q image and vice versa. So it's quite nice. So now the question is, how do we use the Qt components to implement the missing functionality? So now what do we have? Typical AR pipeline is as follows. So we have an image which is taken from a camera, then we detect markers, then we compare it to the database of markers that we have, and then we compute the metrics, the final output, which is the pose of the phone relative to the marker on the image. And from that paper, we only have the third item, which is comparing the image to some kind of a database and detecting markers there and matching it and saying that indeed this is the marker that is present. But everything else is missing. And yeah, so at the beginning we thought it would be quite easy to implement the rest, but actually it was quite a bit of components. So do I have the laser pointer? Nope. This one? Okay. Yeah, great. So at the beginning we still have our marker detector, which is the code from the paper, and it's still there. But we need to add a few things. Namely, for Android, we need to take the image and we need to process it. So we have a camera here, and we have some image processing here. Also, we need to compute the pose using OpenCV. And here we have another component. But also we have another necessary thing is to use tracking from IMU to update the pose to decrease latency. And therefore, we have another component. So there are quite a lot of components. Oh. Right. And overall, we are using around 15 threads. And for a typical tablet, I think we're using tablets from like 1 year old. It uses almost all resources of this tablet. So maybe it's because it's inefficient, but we tried to make it as efficient as it was possible. And in any case, using Qt for that was very beneficial. Namely, it was very easy to implement the missing parts so that there is an app working on Android and detecting the right kind of markers. So specifically, we used key objects. So each one of those rectangles is a key object running in its own thread. And the edges between them, they are signals or slots. So it's a natural mapping between Qt code and this diagram. And also, it was really great to use Qt concurrent. And for the rest of the rendering and image processing, we also use a lot of Qt primitives. So for research, I would say it was a good decision to choose Qt at this point. Now comes the hard part, namely performance. So we implemented all of these components, and we have code from the paper, and it does detect markers, but at the beginning it was very slow. It ran with something like 5 seconds for one frame, the original code that we found. So now we need to speed it up. We have two metrics for that, namely frames per second and latency, which is time for processing one frame. And if we have multiple threads, then there is no direct relationship between them. And to increase FPS, number of frames per second, the key decision is to use tracking instead of matching, namely when we have detected the markers already, we reuse that knowledge, and then at the next frame we use that knowledge to detect them faster. And for latency, we used IMU. And here, Qt was also very handy because we were able to take measurements from Android IMU and integrate them into the format that we needed, namely quaternion. So our application generates quaternion, and also IMU provides one. So together we fuse them and provide a smooth transition. Yeah, and another key decision is to use a lot of GPU processing. Here, slide about how to measure the things that I talked about, FPS and latency. So what we do is we have this graph of key objects, and at the beginning we have a camera which generates images, and then image travels through this graph of key objects that I had before. So there are also multiple paths, so it's like a full graph and not just a line. And what we do is that we mark every image at the beginning, and then each time an image arrives at the end, we take its information and we write it down. And up to our knowledge, we stumbled into this problem that there is no native way in Qt to do this, so we had to write our own extension, but maybe, again, somebody in the audience knows a better way. So this task seems pretty standard. Namely, we have a pipeline, we have key objects which are connected through slots, and they run in different threads, and we want to measure the performance of this whole pipeline. Okay, so what are the components that we want to optimize? The bottleneck was at the beginning, namely image processing. So here we have color conversion and also color thresholding. So since we have these random dot markers, which are just blobs of a certain color which we want to detect, we need HSV thresholding, which is a special kind of color space in which it's easy to detect blobs of a certain color. So this was really slow, and the reason is very simple, that it runs on a CPU, and each pixel is processed separately on a CPU. And before, there was another color conversion step, namely an image from Android camera comes in very non-standard format. It's not RGB. And what we needed to do is to convert it on a CPU. And these were the two key bottlenecks. So the obvious decision is to use the embedded GPU. However, here there are also some problems, and I will talk about them. So initially, an image is a texture on the GPU. So it's natively is on the GPU on an Android device. Then there is an idea to process it on the GPU instead of using the CPU. And it can be done very easy using OpenGL calls. For example, to convert color space, all we need is just a shader. But at the end, what we have is an image in the memory of the GPU. So this is not exactly what we want. The question is how to extract the image from the memory of the GPU. And for example, on the desktop platform, there is a natural solution which would work also on Android. But this is like a standard call to OpenGL. But the problem with it is that it's very slow, because it's copying data from GPU memory to CPU memory. So the time is at least big O of number of pixels, which is too slow. Yeah, but the key insight here is that Android already has a quick connection between GPU and CPU. Namely, it has direct memory access from CPU to GPU data. However, from the software side, it's not well documented. I would say it's not well supported, and it's even more poorly documented. For example, in Java, it's somehow possible to follow the documentation and arrive at a working solution. But in C++, there is similarly trivial problem of getting the image from the GPU to CPU. We run into trouble. Namely, for APIs lower than 25, there is only one way to do that, which is an unofficial hack from a GitHub user I don't know how to pronounce. And what it does is it uses a very specific C++ hacks to access private Android libraries, which would in turn call the function that we want. So in turn, what we want is to call a specific function from OpenGL special Android OpenGL library. This is what we want. However, from the user space, we cannot do that. And the only way to do that is through a special system library call. But for APIs higher than 24, this library is restricted, meaning that regular apps cannot use it. And it's very non-intuitive, and for us it was very not clear why it was made this way. And up to my knowledge, we are the only team who actually managed to make it work on APIs 24 and higher, but again, maybe it's not the case. So the way they did that is that for APIs higher than 27, there is a native solution, documented solution on how to do that. And for APIs lower than 23, you can use this unofficial call to a system library. But for APIs in between, namely 24 and 25, there is a problem because we can no longer use the call to a system library, and we cannot yet use a well-documented solution. So it seems that there is no way to do that. Yeah. So what we had to do is to understand how that hack works for APIs lower than 23 and to make it work for these APIs. And we, after merged it to the original library and wrote a big how-to on how to do that. But for us, it was very counterintuitive that this task was so vital to every computer vision program, but it was not well documented, not from the Android side, not from the, say, NDK side. So, yeah, maybe I'm saying too many bad things today. But it was an interesting experience, but in the end it worked, and I hope that this problem will be somehow resolved. So the way, so here now it's merged to the original repo, and it works for every API that there is, at least up to our knowledge. But if we were to design Android or Qt, probably would add that as a functionality, because I would say that every computer vision app at some point runs into a performance problem, and performance problem is usually solved with GPUs. And when people want to use GPU, they want to copy data at some point, and then they run into this problem, and this becomes pretty hard. Right? So once it's done, the only thing that we need to do is to write a shader, which is a program for GPU, which would run on the GPU, and will process our image, which is already on the GPU, because camera images arrive there. So what we need is to downscale the image. We need to change the color space twice. And then we also use a small hack, which is another layer of tracking. So first layer of tracking is done inside the library that we used, meaning that it remembers the positions of dots that it detected, and then it, when it receives a new image, instead of trying to compute it again, it uses this prior knowledge. But we added another layer of tracking, which speeded things up drastically. Namely, we remember the position of the marker that we had, and we do not process any other part of the image on the next image. So we remember current rectangle with the marker, and we discard, we namely make it black. Every other pixel in the image, which on the previous image was not a marker. So this speeded things up significantly, and we also added this to the shader, and the key trick here is that it does not affect performance at all because it's performed on a GPU. Right? A small drawback here is that on not so performant tablets, it's not possible to run anything else but our app because it uses all of the GPU, but at least it runs fast. So to sum up, what mattered in terms of performance, and maybe it would be a good advice to somebody who is trying to build from scratch a computer vision app using the same tools, is to use GPUs and to downscale the image, also tweak the hyperparameters of the library that there are, and to use the Qt primitives because they really help with not writing a lot of boilerplate code and just writing, for example, one Qt concurrent run, which would speed things up. Okay, so the results are quite good. These numbers might not tell much, but in the demo we'll see that it looks pretty well. And in this table, you can see what actually made this difference. So here we have format conversion. Here we have color thresholding. And if they're done on a CPU, it takes 15 milliseconds for each. And this is the name of the author of the marker detector library. And it only takes the same time as those two combined. So by offloading these to a GPU, we saved half of the processing time, which is quite a lot. And yeah, on a consumer-grade tablet, it does run for quite a long time, but it uses all of its resources. Okay, and a quick note on how to, by the way, I never showed how these markers actually look, so maybe, this slide will clear it. So we have a bunch of dots positioned at random locations, and the only thing that we know are these locations. So we have, for example, a CSV file with locations of each dot, and what we do is that we have an Inkscape extension, and for a scene that we are interested in, we can add these random dots and it will generate this CSV file, so we can feed it to the program. And the program would then take a picture of this, and then do color thresholding, then detect red, and then do its business on detecting, on matching the CSV file to what it sees. Okay. And overall, it's really easy to use now. So at our lab, we used it for one application. And, but I will not talk about that. I will talk about a more general case. So the way it works is that you have an ER component, which you import from our module. And then you can define using Qt3D the necessary objects that you want in your scene. And that's basically it. Oh. Here there is the standard Qt chest from Qt3D. Okay. Yeah, you can find the code on the on our GitHub page. And this is another application of what we did. We have a more complex scene, and it's a bit harder to detect the dots, but the code still manages to do so. So we have the red dots here, and these things, black things, these are in AR, so these are not present on the original scene. And we also have a balloon. So I will not go into details of the game, but it's to demonstrate that even on the tablet, with all of the GPU processing, we can use some more or less complex scene, and it still works. Okay, and we also try to extend it by going into mixed reality. So it's quite easy to implement, actually. What we need is just 2 viewpoints in Qt3D, a bit different positions for each of them, and then we combine them on a single item. So it's quite easy to implement, but we didn't use it because it was too hard for a human to actually watch it. Well, look at this. Like everybody who tried became very dizzy. So this is probably a latency issue, because we have read that less latency and better FPS result in less dizziness. So a quick summary. We'll have a demo after. Yeah, we finished a bit earlier, but I guess it's okay. So we have a library for QML doing augmented reality, and it runs on Android or on Linux. We have gone through design choices of the markers. We have seen the architecture of a typical ER app, and we have seen this particular library as an example. And then we went to performance, and we have discovered that there are certain key moments that arise when one tries to develop a performant application. And we developed our own solutions for this problem, but maybe there are better solutions to this. In any case, profiling code is hard. So I hope at some point it will be much easier to do that in Qt. And yeah, let's see the demos. And the takeaways of the overall of this talk are that it takes time to take a research code, like written by some researcher, and to make it run fast. And using existing well-established frameworks like Qt make it easier, but still sometimes one needs to go inside the libraries and inside some specific solutions and try to make them work in some new conditions, for example, for newer APIs. But overall, the results are quite interesting. So what can be done next? I would say that making it even more seamless is a good idea. For example, in this picture, nobody would imagine that this is a ER marker, but it actually can be used as one. So I would say this is the main direction that is quite interesting. And yeah, now let's look at the demo video. Yeah, this is on Android. Okay, and there is one on, I think, desktop too. Yeah, let's start it. Yeah, so we have a cuboid in the scene, and we also have a chest in the bottom right. It will be visible at some point. Yeah, here it is, and you can see that it looks pretty well, meaning that when I move the camera, you can see chest moving too. So this is the key parameter that we want to optimize for. And also you can see that these markers do not look as conventional QR codes. And when put on a scene, they attract less attention than it would be for the traditional ones. Okay, so I think this is the end of my talk. So thank you. I'll probably close this.
Thank you very much, Sergei. So it's question time. Any question? Oh, maybe everything was clear. Okay, thank you again. Thank you again, Sergei.